Start.
Yes.
Okay, sir. So I'm starting.
Yeah.
Very good afternoon and welcome to one and all. I am Momita from Planet, the designated session assistant for a seamless experience. And Planet is India's most trusted and widely used digital platform with multiple enriching services exclusively for doctors. Planet is very proud to be a digital partner for this event organized by All India Institute of Medical Sciences, Patna. And the topic of today's session is repeated measure ANOVA. So let's begin to this session for which I would like to invite Dr. Venkatesh Karthikeyan sir to take over. Over to you, sir.
Thank you, Momita. A very good afternoon, everyone. It's my pleasure to welcome all of you to our fifth webinar on the series Data Analysis Made Easy with JAMOVI software, hosted by the Department of Community and Family Medicine, AIMS Patna, in collaboration with Merit India and Clarinet. Myself, Dr. Venkatesh Karthikeyan, Community and Family Medicine PG resident from AIMS Patna, and I'll be the moderator for today's event. I'm thrilled to see such a fantastic response to this webinar with participants registering from different corners of the country. As we all know, data analytics has become an increasingly important tool in healthcare industry, allowing doctors and researchers to analyze and interpret vast amounts of data to make informed decisions and improve the patient outcomes. This webinar series aims to provide insight into data analytics and its application in healthcare. I would like to thank our HOD, Professor Dr. CM Singh sir, and Dr. Samshad Ahmed sir, Associate Professor of Department of Community and Family Medicine, AIMS Patna, without whose support this webinar series would not have been possible. Now, I'd like to introduce our resource faculty, Dr. Pragya Kumar ma'am, who doesn't actually need any introduction. However, for those who are new here, I'd like to introduce Dr. Pragya Kumar ma'am, who is an additional professor in the Department of Community and Family Medicine, AIMS Patna. Ma'am has been working in healthcare industry for more than 25 years. She has held various roles in healthcare including Chief Medical Officer, Director Clinical Research, Director Clinical Operations, Director
Venkatesh, you got muted.
Ma'am, you're not audible, ma'am.
Yes, actually, initially in between you got muted. So I was just waiting because I couldn't hear you like announcing, but it's okay now. I may start since I think so. Good afternoon, everyone. And today's session is on repeated measure ANOVA. So we'll start today's session. The data file has been shared with you people. So those of you who have joined with two devices or are on desktop or laptop, you may simultaneously start running the analysis when there is a hands-on, because that will help you to have a better confidence on the data analysis and the interpretation. Because in case of a repeated measure ANOVA, there is it is slight tricky in interpretation. So I would encourage most of you to do the data analysis and running the commands and probably writing the interpretation in the chat box simultaneously. So today's session, we will be covering, we'll start with the basic concepts of repeated measure ANOVA. We'll see the research questions which should be answered using this particular statistical technique. What are the assumptions and hypotheses to check before we go for this repeated measure ANOVA? And today we are going to strict on the one-way repeated measure ANOVA, because repeated measure ANOVA, there are various types depending on the type of independent factor which you take. So we will discuss one-way repeated measure ANOVA in this session. And then we'll see what are the commands in the JAMOVI and how to interpret that output, which is there in the JAMOVI, what to write in your result section. And then at last, we'll summarize the overall commands and interpretation. Coming to the research question, in the it is an extension, you can say that it is an extension of the paired t-test. So those of you who have attended the webinar or otherwise also you have an idea regarding a paired t-test. So basically in pair t-test, what we do, we select a group of people and we measure a outcome variable, which is a continuous variable on 2 occasions. It can be a pre-post, or it can be on 2 different time point, or it can be a 2 different intervention on the same subject. So this is just an extension of that pair t-test, where you have got more than 2 paired value. That means you have got more than 2 values of a dependent variable, which is continuous in nature. So the research question, if my dependent variable is the CRP, C-reactive protein levels in the COVID patients, and I have measured them at first day, 7th day, and 14th day of hospital stay. So had it been only 1st and 7th day, then I would have gone for the pair t-test. But since the number of within subject factor, and in case of the repeated measure ANOVA, the independent, normally we use 2 type of variable. We say independent variable and we say dependent variable. In case of a repeated measure ANOVA, or you have attended the session of one-way ANOVA also, where you have seen that these independent variable we call as a factor. That's why that one-way ANOVA is also known as the between subject ANOVA, and this repeated measure ANOVA, because here you don't have a between subject factor, so that term factor, we will use the term factor for the independent variable here. So don't get confused, because I will be using a dependent variable for the dependent variable. For the independent variable, I will be using the term factor. So in this case, what is the factor or the independent variable? So it is the 3 time point, which is the 1st, 7th, and 14th day of the hospital stay. And what is the dependent variable? So dependent variable, if you see here, it is the CRP levels. So CRP is the dependent, which should be a continuous in nature. So repeated measure ANOVA, the dependent variable should be continuous in nature, and the independent variable or the factor, that should be categorical in nature, and that it should have a more than 2 levels of category. That means it should be a polytomous variable. If a variable has got 2 category, we call it as a binary. But in this case, since it has got more than 2 category, and the more than 2, that means 3 time points are the 1st, 7th, and 14th day. So it is more than 2 time point, and we call it as a factor. Coming to the second research question, if we see this research question, this states that what is the difference in post-operative pain score after 6 hours, 12 hours, and 24 hours of cholecystectomy. I just want to see, like, after which time there is a probably reduction in the dose of the analgesic, or there is a reduction in the pain score. Again, in this case, you will see that there is a dependent variable which is continuous in nature. So that post-operative pain score, which is measured either in the VAS scale or in NRS scale, that is a dependent variable. And the independent variables are the 3 time point, and we call it as a factor. So the 6 hours, 12 hours, and 24 hours, they are again the 3 time points, or the 3, we call it as a factor, and we call it as a within subject factor, because in repeated ANOVA, the same subjects, you are measuring this post-operative pain score in the same set of individual at 6 hours, then at 12 hours, and then again at 24 hours. So it is the within subject, means in the same subject, you are seeing whether the pain is increasing or decreasing over time period. That's why we call it as a within subject. Inside one subject, what is the difference or in the pain score with a passage of time? Or in the other third research question, you can say that does cigarette as a consumption varies amongst heavy smokers after the hypnotherapy program? So in this case, you have taken a group of people who are heavy smokers, and you have done an intervention here, which is a hypnotherapy program. So you did before starting off that particular intervention, 1 month after, and 6 months after the hypnotherapy program. And you want to see whether the number of cigarette, which is a continuous variable, is it varying before, 1 month after, or 6 months after the hypnotherapy program. So the dependent variable in this case is the number of cigarette consumption, and the independent variable, which we call it as a factor. And it is the within subject factor, because the same subject we are measuring at 3 different time points. So in all these 3 research questions, what have you seen? That there is a scale variable. We call this scale term, we also use for the continuous variable. So there is a continuous dependent variable in each research question, and we want to compare the average of this continuous variable across 3 or more time points. Had it been 2 time points, then it would have been a pair t-test. But remember, in the beginning, we discussed that this is an extension of pair t-test, where you have got more than 2 time points, or that independent variable has got more than 2 levels. That's why here the role of repeated measure ANOVA comes. Then coming to the appropriate statistical tests. So if you see if your study design involves any of such research questions, so the appropriate statistical test for you is a one-way repeated measure ANOVA. Now, I hope you have understood by this time what is a repeated measure, and we'll discuss later on also what is a repeated measure. Repeated measure is same individual, you are measuring more than 2 time point, and it can be same individual, more than 2 interventions, or in case of a randomized control trial also, you can apply this test. So this is the repeated measure. Now, repeated, there are various statistical tests which we apply for a repeated measure data, because this data set would be repeated measure. So you can see there is a list of statistical technique. The repeated measure ANOVA we are going to discuss today, but there are other statistical technique also, like mixed effect model or linear mixed model, multivariate analysis of variance, generalized estimating equations, time series analysis, and then there are non-parametric tests like Friedman test also, which you will see today in the JAMOVI, that also we use for the repeated measure. So, but today we are restricting on the first option, which is the most commonly used, and it is a simpler test to apply and to interpret. The other options like mixed model and multivariate and generalized estimating equations, that are a little higher, and when it has got some assumptions, like if there is a lot of missing data, or one of the assumptions does not holds true for the repeated measure, then you go for these sort of analytical technique. But today's we are restricting ourselves to the first option, which you can see as a red bold one, like that is the repeated measure ANOVA. So now just ponder on this data set for a few seconds. So now what can you see? Here I'll just help you to see. So this is the first column, which is a serial number. So there are 12 patients here. The second column, you can see it's the name of the individual. So name, like you can see AK, BK, CK and DK. So I have measured their weight at baseline, all these 4 individuals. Again, I have measured at 3 months their weight, the same individual, because you can see AK, BK, CK and DK. And then again at 6 months, I have measured their weight. So it's 62, 72, 75 and 70. So you can see that there are 4 individuals and I have taken their repeated measurement and their weights are like this. So can I use a standard ANOVA, or like you can say that one-way ANOVA for analyzing this repeated measure data? Because what I can do, like I can treat all these individuals as different individual. But again, if you recall, in a one-way analysis of variance, we have read that the observations. There should be independence of observation. That means if you have counted one individual in one column, you will not count that individual again. But here you can see you have counted the same individual thrice. So that means your independence of observation, that assumption is not met. So you cannot go ahead with such data set for the repeated measure analysis, for the one-way ANOVA analysis. So choice of test would be the repeated measure in this case. And definitely the data arrangement would be different. In this case, you can see we have arranged it differently, but in case of a repeated measure, one row will signify one case. That's there in the JAMOVI, and we'll see. So now coming to the study designs, what are the different types of study designs which are suitable for this repeated measure analysis? So in the first type of repeated measure, this study design, you can see the difference of any dependent variable across 3 time points. Like you can see the change in blood pressure during an exercise training program at the beginning, midway, and post-intervention. So here, it's only the time which is there as a within subject factor or independent variable. The second type of study design could be difference between 3 or more conditions. If you are measuring a cholesterol level before one intervention and after intervention, and there are 3 groups. So the first group is 6 weeks. That means in the same individual, you are using a 6-week control, exercise training, and dietary control, but on the same individual. So in the same group. So you are obviously after a washout period, you are going to use these. So this is another type of study design. The third type of study design is the difference between 3 or more change score. So you have measured like pre and post of each intervention, and you have got a change score. So you can do a repeated measure analysis of variance for this change score also. So these are basically the 3 type of designs which we take for this repeated measure analysis of variance. So is time always a requirement in repeated measure analysis? Please answer yes or no in the chat box. Okay. So answer is yes. But in this case, what about, because it's a repeated measure, if you are just seeing something before and after, in this case, in the second case, difference between 3 or more conditions, like you have measured one individual blood pressure, probably with the this automatic, one with this sphygmomanometer, and third probably the intra-arterial. In that case, what will you say? Do you need time in that case? Like I said now, the difference between the 3 or more conditions. So like for intervention, definitely you need a time. But for things like if I'm just using any in the same set for any teaching technique, or you can say any investigational thing, like I just gave you the example of blood pressure machine. If I am measuring the blood pressure using 3 different instrument, and I want to see like there is any difference in the 3 intervention or not, because I'm using the same set of individual. So yes, you are right. If it is a randomized control trial, and if the intervention, definitely if it desires that there should be a passage of time, because for intervention, for such interventions where you desire a passage of time, then definitely the time will be an variable. Like remember in paired t-test, we have discussed that you can take a right arm and a left arm, probably that also as a paired data. So in such cases, obviously those will be a very less common one. Then time may not be always a requirement, but in most of the study you will see, because this repeated measure design is like pre-post intervention most of the time. Then you will see that yes, it is a requirement in most of the cases this time. Now, what are the benefits of this repeated measure ANOVA? So first is it is very cheap and faster. So cheap in what context? Like you have to recruit only, like I can say if my study involves, I can recruit 20 individual, and then I don't need to go for another 20 individual. I can do the intervention first and then some washout period, intervention second, some washout. So they may act as their own control and the variability is less. So it is faster. And again, because of the same subject, the variance in the data, it will be a subject, it will be very less. And that's why it makes easier to obtain a smaller p-value with that sample. So that's the benefit of repeated measure ANOVA. But again, in this case, there are some limitations of this repeated measure. So what are these limitations? Limitations would be, first is the practice effect or learning effect. We'll see one by one what are these practice effect or learning effect. The second would be the latency effect. And the third is your carryover effect. So let's see one by one what are these three effects. So example of practice or learning effect, let's say this example of cognitive training for memory improvement. So a researcher is investigating the effect of a cognitive training program on the memory improvement in older adults. The study involves assessing the participants' memory performance using a memory test before the training, immediately after the training, and then again after 3 weeks of the training. So the pre-training memory score, let's say the mean is 60. The post-training memory score is 65. Just don't assume that it is a percentage. Just don't read it as percentage. It is 60, 65. And the mean memory score at week 3 is 67. So you will see that after 60 to 65, there is a huge increase. And after at 3 weeks, it is 67. So analysis, it has shown that there was an increase, but that increase may be due to the time also. Because when you have given that memory test for the first time, the person was not very much comfortable using that test. But over the passage of time, he has now understood how to approach that particular test. So with that multiple measurement, he's now used to apply that test. And that's why it is difficult for you to say that it is alone due to your intervention. It can be due to the practice effect also. Because initially when you have given it before the intervention, obviously the person will find a little difficulty in attempting those questions. But again, if you are using the same tool, next time definitely he will be more versed because he is now practiced it once. So this masks the overall effect. So this is example of the practice or learning effect, which we see in case of a study design using this repeated measure ANOVA. The second type is the latency effect. What is the latency effect? So let's say in this example, a researcher is studying the effect of a new diet and exercise program on weight loss. The study involves measuring participants' weight at the beginning of the program, at the end of the program, and then again at the end of the 3 months after the program has ended. So in this case, you will see that the baseline weight was 180 pounds. At 12 weeks, it was 170. And then again, 3 months after, you will see it is 168 pounds only. So after like even 12 weeks have elapsed, but there was a reduction of only 2 pounds. So you will see that the researcher needs to think that maybe initially that program has worked. But after this 12 weeks, you may need to put another strategy into it. Probably that, compliance or probably some more intervention needs to be added to get a further result. So this is known as the latency effect. So that repeated measure, if you measure this data, you might say, if you are measuring it at baseline and at the 12 weeks and 24 weeks might say that the intervention was not very effective. But this is only showing the latency effect. And there are ways to address these latency effect. We'll discuss it. And the third is the carryover effect. Now, what is this carryover effect? So carryover effect is also known as the residual effect. And it happens when the effect of the previous treatment or condition, it is still continuing and you have added a new treatment. Like in this example, a clinical trial is conducted to evaluate the effect of two different drugs, drug A and drug B, on lowering the blood pressure. And if the study uses a crossover design where each participant receives both drug in the two different phases, you know, a crossover design with a washout period to minimize that carryover effect. So blood pressure was measured at participant received drug A for 4 weeks. Then there was a washout period of 2 weeks. And then in phase 2, the participant received drug B for 4 weeks. So if you see the baseline blood pressure, it was 140/90. But at this phase 1, end of the phase 1, the mean was 130/85. But if you see the post-treatment blood pressure with the second B intervention, it is definitely less than 140/90, but it is more than the phase 1. So it has now increased to 135/88. So it is showing that definitely there is some effect of the first drug which is there, and then you have added the second drug. So these are some of the problems which are existing with such repeated measure design. So what are the solutions to address these problems? So first is the counterbalancing. Now, what is the counterbalancing? So you just vary the sequence in which the participants experience different conditions or time point. Like in that cognitive training study, you can change the order of the different participants or group across the 3 assessment time point. In case of there's again one way to control this is to have a control group. If you have a control group where there is no intervention, then you can see whether it is the learning effect, practice effect, or actually the intervention, because the difference from the control will tell you whether it is the practice effect or it is the actual intervention per se. In case of a washout period, you should add a delay between the different time points to reduce the carryover effect of intervention. And you can also use the alternate forms, like in that practice effect, if you use a different version of assessment tool, like for memory cognitive, you have used first tool for the first time and then the second tool in the next time. And definitely there should be a high sensitivity between in respect to the first and second. There are some statistical technique also to carry over this problems. I mean, as a solution of these problems. And one of the statistical technique is the analysis of covariance. So like if you have a covariate, if you have got a lot of factor, and if you want to balance between these 3 problems, then you can apply the analysis of covariance also to address this problem of latency or a carryover period or for a practice effect. So now coming to the null and alternate hypothesis. What is a null hypothesis in case of a repeated measure ANOVA? So in this first, you can see the repeated measure ANOVA say that there are no significant differences between the dependent, the dependent variable in the 3 different time points. An alternate hypothesis states yes, there is a difference between the dependent variable and at the 3 different time points. So this is again stating this null hypothesis in a different way. There is no difference in population mean of repeated measure, that all are equal. And in alternate hypothesis, we say that there is a difference in the population mean of repeated measure. That means at least one group population mean is not equal. Now coming to the assumptions, because in all such analytical, or we can say that hypothesis testing, we have got assumptions, and assumptions, these satisfaction of these assumptions are very much needed before you go for a repeated measure ANOVA, because violation of these assumptions may lead to erroneous result and erroneous interpretation. So the first assumption is that the dependent variable should be continuous. And in the example of research questions, we have seen how a dependent variable should be. Like you can see there we discussed a pain score measured at 3 different time points. Number of cigarette smoked, again a continuous variable. So the dependent variable should be continuous in nature. And there should be at least one within subject factor that consists of a 3 or more categorical levels. And we have discussed in the beginning that we call factor all independent, we call independent variable as a factor. And since here the same set of individual are being measured, that's why we call it as a within subject factor. And then another assumption is there should not be a significant outliers in the dependent variable. So in JAMOVI, you cannot do this test in the option of repeated measure ANOVA, but those of you who have attended our descriptive statistics session, you know that how do we test for this outlier. So outlier basically we do with the testing of a box plot. So we plot a box plot, and then once we detect those outliers, there are ways to handle those outliers. If the number of outliers are few, you can decide to keep it in your analysis, or you can remove that outlier and rerun the analysis, or you can replace the value of that outlier with the next highest value. So there are 3 ways to tackle these outliers. But whatever you are doing, you have to mention in your statistical analysis and result section. That is must, because that helps the reader to understand the result and interpretation in a better way. So there are 3 decisions. Whatever decision you take, that is up to you as a researcher, but just mention it that these many numbers of outliers were there. Coming to another set of assumptions, the 4th assumption is like dependent variable because should be approximately normally distributed in each level of the within subject factor. So this also we test with the help of, you can say that normality testing, and we have seen that in the session of descriptive. Here also in the basically in the repeated measure ANOVA option in the JAMOVI, there is an option of this QQ plot. So this basically calculates the QQ plot, but the option of Shapiro-Wilk is not there here. So if your data set is small, like in today's data set, you will see that I have taken only 10 number of people just to make it simple. So then this QQ plot will not be an appropriate way of normality testing. It's better to go for a Shapiro-Wilk. And in case of this repeated measure ANOVA or one-way ANOVA, basically we test the error. So now what is an error? We all know, those of you who have a background of regression, may it a linear regression or a logistic regression. So basically what is an error? Error is like what is predicted and what is actually observed. The difference between these two, we call it as a error. So in case of this also, all these normality testing and outlier, basically we test it for error, not for that individual this thing per se. That's why it's better to use the option of repeated measure ANOVA QQ plot to test for this normality assumption. And again, this is just a repetition that there should not be significant outlier in the dependent variable. And the next assumption is this assumption of sphericity. What is this assumption of sphericity? That the variances of the differences. So remember, we discussed this variance and post hoc test in detail in the last session, which was on one-way ANOVA. And there we have seen how to calculate variances. So basically this variances is the sum of square. How to calculate this sum of square? So you calculate a mean and then you deduct this overall mean from the individual mean. You square it and you divide it by the degree of freedom. Degree of freedom is the total number of individual minus 1 depending on, and then there are 2 type of variability. There is a within subject variability and there is a between subject variability. So these all concepts we have discussed in the session of the one-way ANOVA. So I'm just refreshing by saying those concepts. Those of you who have joined this webinar for the first time, You can also go and see that concept of post hoc. What is a significant post hoc? Where we explain that with an example of that money box, where the difference we have said that the 500 rupees, if the difference is that much, we will consider it significant. So you can go and see that. But for the purpose of this today's session, you know what is a variance. So whenever we say variance, it should click to your mind what is a variance. So the variance is basically an overall mean, and we deduct it from the individual mean, we square it, and then we divide it by the degree of freedom. That is the variance. So this what this sphericity says, because you can recall, I will again show this in the data set, that the individual variables are there, and here you can see that the variance, there will be a variance in one point of time, there will be variance in second time point, and there will be variance in the third time point. So there will be difference, like if there are time point 1, 2, and 3, so there will be difference in variance between time point 1 and 2, time point 2 and 3, and time point 1 and 3. So the difference between all combinations of level of then within subject factor, it should be equal. So that difference of the variance should be equal. That is one of the very important assumption of a repeated measure ANOVA. And if there is a violation of this assumption, then there are two ways to deal with it. Either you can go for the linear mix model, or you can apply the correction, which we'll see in JAMOVI. That there are two ways to handle this problem if the assumption of sphericity is not met. So this is tested in the JAMOVI by the Mock-list test of sphericity. And again, I will explain this when we will see the data set. So this is the Mock-list test of sphericity, and Mock-list test of sphericity is if the value of significant value or the p-value is less than 0.05, then we say that the assumption of sphericity is not met. And remember, we have like also fixed one rule that you will see that most of these named tests, whether it is a Shapiro-Wilk test, or in case of a homogeneity, we use the Levine's test of homogeneity of variance, or Mock-list test. So all these tests you will see now that if the p-value is more than 0.05, then only the assumption is met. So here we don't want our p-value to be less than 0.05, because that is going to create problem for us. We'll have to go for adjustments. We'll have to go to the, log transformations and all. So we don't want that. That's why I want my Mock-list test of sphericity assumptions to be met. And for that, I want my p-value to be more than 0.05, not less than 0.05. Why? Because in all these name tests, we call it as a null hypothesis. In null hypothesis, we say that the variances are equal. That's why I want my alternate hypothesis to be rejected. And that's why I want my p-value to be more than 0.05. Now, if this assumption of sphericity is not met, then we apply Greenhouse-Geyser correction or the Hunfeld correction. So in case of JAMOVI, you will see that if the value of this if the assumption is not met, then what will you do? Definitely you have to go for the correction. So there are two types of correction: Greenhouse-Geyser correction and Hunfeld correction. So if the value of Greenhouse-Geyser is more than 0.75, then we should use the Hunfeld correction. If it is less than 0.75, then we should use the Greenhouse-Geyser correction. Don't get afraid by these all named thing. Once you see the JAMOVI interface, it will become very easy. So don't get all these terms, don't get perturbed or get fearful with all these concepts. Just remember that if the p-value for the Mock-list test of sphericity is less than 0.05, in that case, you have to go for the corrections. Now coming to the effect size of this. So remember, we discussed the effect size also. There are various ways to say this effect size. In chi-square, remember we discussed that phi and Kramer V as a measure of effect size. In case of that independent sample t-test, we have learned the Cohen D as a measure of effect size. And in case of ANOVA, generally we use the eta square. And there are basically 3 types of eta square, which is a measure of effect size in case of ANOVA, which is the analysis of variance. In JAMOVI also, you will see there are 3 options and you have to click one option. So just for explanation, I have included. So what is a eta square? So basically, eta square is the percentage of variability of the dependent variable accounted by that independent variable or factor. So if there is a lower sample numbers, like we'll see today's hands-on, where we have taken only 10 individual, you will get a higher eta square value. So this is a problem. Then again, the other concept is the partial eta square. Now, what is a partial eta square? So basically, it considers the degree of freedom also, and it is very important when you are having a more than one factor. Like today's, you will see that time is one factor, then we have taken gender also, you can take treatment also. So if you have gone more than one factor, then you should go with this partial eta square. And then there is something known as the generalized eta square. So this generalized eta square applies when there are more levels of the factor. Like we have, if there are 5, 6, 7 levels of that independent variable or the factor, then we go for the generalized eta square. But for most practical purposes, we go for this partial eta square. And that we generally click in the JAMOVI interface. Now, what is the interpretation of the various values of this partial eta square? So if the partial eta square is 0.01, we say that it is a very small effect size, which is not of very clinical significance and not a practical significance. Now, if the eta square is 0.0c, we say that there is a moderate impact of the factor on the dependent variable variance and the factor has a noticeable influence. And if it is like up till 0.14, definitely we say that it has got a large effect size or a substantial impact of the factor on the dependent variable variance. And it is a strong predictor and its influence is likely to be a practical significance. And in these all these sessions, we have discussing that along with p-value, we also give the effect size in all these hypothesis testing, whether it is independent sample t-test or chi-square test or analysis of variance. We should mention these effect sizes in our. And in JAMOVI, it is very easy. You just have to click and it will give you, and then you have to interpret. Definitely, interpretation is the task which we have to perform. So now there is one thing which we call it as an interaction. Now, what is an interaction basically? So here you will see that we have discussed in all the examples that there is a one independent factor, which is the time. Let's say if we have got one more factor, like gender. So how do we define interaction? So basically, there is a dependent variable and there are 2 independent variables, maybe gender and time. So if the effect of time is same across the 2 gender, then we say that there is no interaction. Or you can say the other way around also. If the gender has got no role in that timing, in the variability, then we say that there is no interaction. So interaction refers to a situation where the effect of one independent variable on the dependent variable changes based on the level of another independent variable. So here, one independent variable, like we say that usually we take time. So that is there. Dependent variable, if it is a weight reduction, and then the another dependent variable is the plan. There are 2 plans, weight reduction plan A and weight reduction plan B. So if I clarify it in a simpler language, then I can say that the relationship or the variables or this weight change is not same for all groups at all time points, and these 2 are interacting with each other. And we'll see, we understand this graphically, and there is a statistical way to test this also, because this interaction is very important. And we'll see today I will be showing you two types of repeated measure ANOVA. One repeated measure ANOVA when I have taken only time as a between subject factor. And here I have taken another independent variable, which is the gender. So then I will have to see, like, is this change is same across the male and female, or there is a difference in male or female? Because as such, this repeated measure ANOVA, we say that it is an omnibus test. What do we mean by this term omnibus? So whenever I say that term omnibus, that means it concludes that yes, there is a difference between the pair, but which two pair, at what level? For that, you need to apply these interaction term, and you will have to see the post hoc analysis also. So post hoc, remember in one-way ANOVA also, we have learned about this post hoc, like which two groups or which pair is showing a significant result. Here also we'll see the post hoc. So now, for example, all of you please see this graph. What is this graph? Basically, here you can see there is a x-axis and there is a y-axis. So on the y-axis, it is the weight in kg and this is the weight reduction. Basically, it is not weight actually, it is weight reduction. So on y-axis, you can see there is a weight reduction. On x-axis, you can see there are three different time points: 3 months, 6 months, and 9 months. So I have taken one group of people and they are like, first I have given them a weight reduction plan A and then weight reduction plan B. So at the end of, or maybe I can say that there are two individuals. So in this case, there is a intervention arm 1 and there is an intervention arm 2, because this repeated measure ANOVA, we use it in case of a randomized control trial also. So you can see here that in intervention arm 1, which is the weight reduction plan A, at the end of 3 months, the weight reduction is 5 kg. And in weight reduction plan B, at the end of 3 months, it is a 3 kg loss. At 6 months, it is the 8 kg, both same. And at 9 months, in intervention arm A, it is the weight loss is 10 kg, and intervention arm B, which is the plan B, the weight loss is 12 kg. So what will you say? Is the effect of weight reduction plan on weight loss is same at all time points? Please answer in the chat box. What is your interpretation? Yes, no, or can't say. So Shweta is writing no. One doctor, then Renibi, Rutvik, Brahmata, Chatra, Patil, Shruti, Vinu, Deepti. So I think most of you have written it correctly, that yes, you can say that effect is not same, because you will see that initially the plan A was carrying more effect. Then at 6 months, both became equal. And at 9 months, the plan B, the weight reduction was more in plan B. So definitely there is an interaction between two. So whenever you see such lines, we'll see today, this is a plot of estimated marginal mean. We'll see the concept of estimated marginal mean also. And here you will see that it is crossing. So that means that there is definitely an interaction between these two. Did you get it? Now see this graph. This is again the same graph where we have changed the values. So you can see the weight reduction plan A and B. So at 3 months, you can see that 5 and 3. Then again 6 months, 8 and 6. And 9 months, the reduction is 10 and 8. So Chatra is saying, ma'am, but at last both planned 23 kg weight loss. Okay. So you are saying in the previous one. So she has added, I guess, like you know, so that overall reduction that we are not considering, because we have just taken as a, like, made this data probably. And again, you can see that here we want to see the effect of both the intervention at various time points. So since we have created this data, so maybe that's why you can say that overall it is same, but ultimately we are not going to do it at the end of this. Okay. So now coming to this thing. Next example. This one. So you can say that plan is effective. But my question is the effect of weight reduction plan on weight loss is same at all time points? So Reneby is writing no. So there are mix of answers like yes and no. So what can you see? These lines are parallel. So at all time point, you can say that the plan A was better than plan B. In this case, because the lines are parallel. So whenever in graph you see that lines are parallel, that means there is no, at every time point, the treatment plan A is better than plan B. Okay, any problem with the voice? Am I audible correctly
It's
to
fine,
all the...
ma'am. It's fine, ma'am. In between, there was little glitch, ma'am. It's fine now.
Okay, let me, because I tested today. Okay, thank you, Venkatesh. So we see that lines are parallel. That means there is no interaction between the plan A treatment options and the time point, various time points. And you can see that the difference is 2 kg in all the 3 time points. So we can say that, yes, there is no effect of weight reduction plan. It is same at all time point. How about this? Yes, so you can see that. So what is your answer? Is the effect of weight reduction plan on weight loss is same at all time point? In the previous example, I guess Shraddha has got some question, like it is 2 kg. Yes, it is there, but that treatment A, it is maintaining that loss. Like loss is always 2 kg higher. So we can say that the plan A is better. That's what the interpretation would be. Shraddha, I hope it is clear to you. And then the next option is, you can see here, since the lines are crossing. So in any point of time, if you see that the lines are crossing, then you say that, yes, it is not same at all time point. And you can see the values also. Initially, both was at 3 months, the reduction was same. At 6 months, the reduction was more in the plan A, and at 9 months also it was more in plan A. In this case also, again, you can see the same thing, that the effect of weight reduction, this plan on weight loss is not same at all time points. And this is again the same. Now, if my question, now I have changed my question. In which study there is a significant weight reduction across weight reduction plans? So you can see there is a figure 1. This is the same previous figure which I have used, like difference of 2 is maintained over time. And in this case, you can see here, the difference, the gap is lessened here. So can you say by seeing these plots regarding the significance? Yes, true. We cannot say, because the significance testing will only be seen when you see that table. So by the graph, you can only say that whether there is a interaction or not. But if that difference of that weight change, which we were discussing in the beginning, whether that is significant or not, that you will have to see from the post hoc comparison. And we'll see today how this interpretation changes. Like interaction is significant, but you will see that the difference of that value is not significant. So this was the effect of interaction, and we'll see what is an interaction in JAMOVI. Now let's understand this concept of marginal mean. So what is a marginal mean? There is a arithmetic mean which we all know. What is a mean? Now, the second is a concept of marginal mean. So marginal mean is basically if there is no missing data. So you know that repeated measure, because you measure the subjects at more than one time point. And again, in case of a randomized control trial also, if you are measuring the two arms for a continuous variable, there will be missing data. So if there are missing data, then the normal mean is not a better way to estimate it, but it is the marginal mean which you should have. And if there are unequal sizes, so generally you will see that in randomized control trial, there are unequal sizes. So you will have to see the concept of marginal mean. So now let's see, a researcher plans to compare the effect of weight reduction interventions. And there are two interventions, diet and exercise. And I want to see the effect for gender also on this. So the data is as follows. This is the column for gender. So there are 3 to 5 males and 5 females. And this is the intervention like diet, exercise, diet and exercise. And this is the weight loss like 3 kgs, 5 kgs, 6 and 7. This is just random. So in this case, you will see here, the same data can be arranged like this. So you will see that, please see this carefully. We have tried to explain the concept of marginal mean, because in case of a repeated measure ANOVA, you will see there is a box of estimated marginal mean. So how this estimated marginal mean is different from the normal mean and why we use this term of marginal mean. So we have tried to explain that. So can you arrange this data like this? So I've just, what I did, male and female, 2 interventions, diet and exercise. And I have taken these 3 values, like all these 3 diet together, male in one, this thing. So 3 kg weight loss. In female, on diet, it was 7 and 8 kg. On exercise in male, it was 5 and 6. So if you see this thing, previous one, you can see this is 5 and this is 6. So these 2 values, I have written it like this. And in female, the exercise caused like 3, 5 and 7. So have you understood up till this point? I have arranged this data like this. Is it clear up till this point? I can see 1 yes. Shweta is also writing yes. Rahul, Manisha, Renebi, Dipti. Okay, thank you. So you can see that we have arranged data like this. Now, if I ask you what is the mean weight loss with dietary interventions, I am not taking gender into account now. I am only asking you mean weight loss with dietary intervention. So can you all please calculate and tell me? You can use your calculator. Or you can, those of you who are good at maths, you can do it verbally also. So 339 plus 15, 9, it will be 24 by 5. So it will be 4.8. Yes, very good. All of you are right. Now, if I ask you this question, what is the mean weight loss with exercise intervention? Then what will be your answer? All of you please redo this activity for the exercise group. So yes, Shreya have written up till Sagar 5.2 and Binu, Namrata, Zoha, Shraddha, Satish, Chandrasekhar. Okay, Ajit, all of you are right. It is 5.2. So this is one way to calculate mean. Now, so in this previous one, I have not taken this gender into account. It is the like overall across diet and exercise. This is one way of using the mean. Now I have split it like this. So what I did like, I took mean of these 3 and I have written here like in male, the diet, the mean exercise loss was 3. Similarly, I have taken this 5.5 as a mean of 5 and 6. And in female, I have taken this 7 and 8 mean as 7.5. And in exercise, I have taken as 5. So now, if I ask you what is the mean weight loss with dietary intervention adjusted for gender? So now if I ask you this question, what will be your answer? So definitely what will you do? 3 plus 7.5, it will be 5.25. And if same question, if I ask you this in exercise group, it will be 5 plus 5.5. That means 5.25. So in this case, you can see that this is same. Whereas in the previous one, if I was not taking the effect of gender, then the mean was different. So this mean is the mean which we call it as a normal arithmetic mean, and this mean is the estimated marginal mean, which you have calculated here. This we will also try to show you. This is mean and this is estimated marginal mean. So let me show you with the Excel also. So this we have. So can you see this Excel sheet? So here first focus on this part of the view, this part. So you can see the question is change in hemoglobin level after 1000 microgram of, it's milligram actually, IV FCM. FCM is the ferric carboxymaltose administration in pregnant women over various time point. So this is an intervention study probably, and I have taken this case 1. I have measured the hemoglobin level at baseline, it was 5. I have given the 1000 milligram of IV FCM, then measured the hemoglobin at 1 month 7 and at 3 months it was 11. Similarly, for the second individual, I did the same, and third again I did the same activity. So if I measure this, so you can see this is, one is this value. So this is the average hemoglobin level at baseline. It is the average of 5, 7 and 6. This is the average of 7, 8 and 9, and this is average of 12. So this 8.7 is the average of average. And if you see this value 8.7, this is like, you can see average of all these 9 cells. So if there are no missing data, then you can see that these both estimated marginal mean, we call it as an average of average also, this one, this and this will be same. But if there are missing value, like you can see I have deleted one value here. So you can see since I have used the formula, in this case, the estimated marginal mean will be different from this mean. Again, if I delete one more column here, you can see that this mean has changed. So this mean and this mean is not same, 8.3 and 8. So in this case, you will see that the mean and estimated. So that's why, because of this missing data and because of the unequal arm, because you will see that most of the time the cells, there will be unequal arm, and that's why we use the concept, or we use the estimated marginal mean to report our result. So estimated marginal means are the group means after having controlled for the covariates. So now it's the time for hands-on. I'll show you all these concepts which we have just learned on JAMOVI. So we have used 2 data sets. The data set has been mailed to you, and it is there in the chat box also. Those of you who wish to do the analysis with us, you can do it simultaneously. And because before I go for the hands-on, there's an announcement for the next webinar on the same, I think, second Tuesday, which is on the 12th of September from 2 to 3:30 p.m. And this time is 2 to 3:30, or it's 3 to 4:30. Okay. So it's 2 to 3:30, and it is on the logistic regression, binary logistic or binomial logistic regression. So now let's run the analysis on JAMOVI. So I have all of you, those of you who have not downloaded JAMOVI, you can go to the Google, type JAMOVI, and there you can download the solid version. So I'll go to this data set. There are 2 data sets here, you can see. So I will, first I will open this data set. So this is, I will just show you, we have just created this for demo. So let me control. Let me delete this. I will move this back. Somehow this got saved, so that's why it is showing you. Yes. So now you can see, or let me delete all and delete. Now this has gone. So this is my data set. And if I show you the variables, you can see these are the variables like age, and there are 4 measurements like systolic blood pressure in summer, spring, autumn, and winter at 4 time points, and similarly the pulse rate also at 4 time points. So I have just unchecked all this because all the variables are selected. And then I'll go to this data. This is my data set. And then coming to the options of analysis. So we have seen up till now descriptive. In the exploration, you see the descriptive, we have done that. T-test, we have learned like independent sample T-test, paired sample T-test, and one sample T-test. Then in the frequencies, we have learned in the second webinar regarding that chi-square test of association, goodness of fit. And then ANOVA, in the last webinar, we have seen this one-way ANOVA. Now today, it's the repeated measure ANOVA. So I'll click on this repeated measure, and then you will see that something of this, there are 2 windows which appear. So in case of a repeated measure, this is RM factor 1. What do you understand by RM factor 1? RM factor 1 means that it is a repeated measure factor 1. So here you have to level the factor. So I will level, if you want to write it at spring, so you can write it at like measurement in spring, or if you want to write like systolic blood pressure, so you can write SBP in spring. You have to write here, you have to create this, then only you can see. Once I write this here, you will see there is an appearance of this repeated measure cell here, you can see. So that's why you need to create this first. Here also I will write SBP in summer. You can take a decision and you can only go with levels also if you don't wish to write. But just because in output you can see it clearly, that's why I am writing. Then you can write SBP in autumn. And then in level 4, you write SBP in winter. Now you will see that you have created all these cells, and all these repeated measure, they are appearing here in this window. Now I need to move each and every value. So this is my value for 1. So I have entered this. Now I will go to this. So if you see this blue color, that means this cell is active. Can you see there is a blue, this thing, color highlight here? That means this box is active here. So now I will move this summer to this one. Then I'll go to third autumn one here, and then I'll go to winter and here. So I've entered all these values. So once you enter this, it gives you a overall effect of ANOVA. You can see, we'll come to this later. Let me show you the commands. So what we discussed, that we need to check for the assumptions before we run the one-way ANOVA. So coming to these assumptions, can you see there are models also? I'm not going into the model now. We'll come to it later. Coming to these assumptions. In assumptions, you can see there is a sphericity test. So I'll click this sphericity and there is a QQ plot. Homogeneity I am not using because there is no between subject factor. Now coming to the interpretation of Mauchly's test of sphericity. So this Can you see the value? So all of you, what is your interpretation? Is this p-value is significant? Then what does it say? Whether the assumption of sphericity met or not met. Yes, Smita is writing significant. Yes, not met. Agree. So since it is significant, so we can say that the assumption, it is not met. So now what should I do? Then I will go for this greenhouse gazer. And in that case, I will click this sphericity corrections. So remember, we thought that if its value is less than 0.75, we'll take this greenhouse gazer. So I'll apply this corrections, and then it will show you the value, and you have to take this. So in post hoc, we'll use this. Now, assumptions, the second assumption was the QQ plot. So QQ plot, it is here, and you can see it is approximately normally distributed because the individual data point are across this line. Although it is a but 10 data, but it is not a 10 multiplied by 4. That means the total of 40. And I said that it basically, if you see it standardized residual. So remember, we discussed the concept of error. So basically it plots the error, and then based on that, we say that it is normally distributed or not. So it is approximately normally distributed. If this was not normally distributed, then I would have to go for this option of Friedman. Can you say there is a non-parametric option of repeated measure ANOVA Friedman? So if it is not normally distributed, I would have to go for this repeated measure ANOVA type Friedman. But since it is normally distributed, so I'll go with this one-way repeated measure ANOVA. So I have checked for this. Now I will go with this effect size. So you can see we discussed this generalized eta square, and partial eta square. Partial eta square is more commonly done. So I have clicked this. And if you see this, so it says that yes, it is significant. So p-value you can see. So the values of the blood pressure at various time point between the 4 season, that is varying with a p-value of 0.02, and this is 0.26. That means moderate effect size. Remember, we discussed the effects. So no, it is 0.14. It is more than that. But we also discussed that if the sample size is less, this goes very high. So that's why it is eta square is so high here. But if you see the p-value, it is 0.09. And how do we see the value of f? So this f statistics, if you see this value of f, this is basically calculated the mean square of this repeated measure factor 1 divided by this residual. So this residual value is A189.79. So if you divide this 652 with this 189.79, it will give you the value of f. And this is since greater than the critical value of f, that's why it is significant. So I can say that this is the, there is a significance in this repeated measure ANOVA. But remember, we discussed that this repeated measure ANOVA is an omnibus test. Now I don't know with this value, like which two pair is significant. Is it autumn, winter, or it is spring, summer, or which two? So I will have to go for the post hoc, and that we'll see. Again, you can see something here as a type 3 sum of square. So this type 3 sum of square, basically we use this, and this is the default. Generally, you can change this here, but generally we use this whenever there is an unequal size and there are more than one factor, then we go for this type 3 sum of squares. So now coming to this, and here because there is no between subject factor, it is only the time, the 4 seasons I am measuring. Now coming to this model. So here the model, it is the repeated factor, it is there already it has taken. So you don't need to do anything. I have just closed this. Coming to this now, here, remember, we discussed that you have to report the greenhouse gaser because the assumption of sphericity is not met. So you will report this degree of freedom. This one and the other one will be the residual. So these will be the 2 degree of freedom which you are going to report. 1.97 and 19.67. Since the assumption of sphericity is not met, so the greenhouse gaser correction was applied. And remember, we discussed that if the value of greenhouse gaser correction is less than 0.75, you will go with this. Otherwise, you would have ticked this Hunfeld. But there's no need for Hunfeld in this case. Now, so have you understood up till this point? Then I'll go with the post hoc and estimated marginal mean. All of you, Anil Kumar is writing, you should select. No, it is less than 0.75. If you see this now, it is less than, you can see the value of greenhouse gaser is 0.66 here. Can you see this one? So if it is less than 0.75, then you don't need to go for Hunfeld. With correction, it is not significant. Okay, it is, you can say it is just significant. Yes, you are right that it is 0.05. It has become 0.05. But again, I said that this is a problem with, since there are only 10 data set. So with that small sample, there can be, if you have got a very big data set, then it is not going to be a problem. Okay, so Shweta is writing, why we divide mean square by residual value. Okay, Shweta, here what is there? This residual is the overall error. So this model calculates the value of residual by having a observed and projected. So the difference between these two, on the base of that, it calculates the overall mean square. And in case of a repeated measure ANOVA, the residual is the error, which we cannot explain on the basis of factor. That means besides season, there are other factors also which is responsible for this variation. That's why the value of error is high here. Even it is, you can see it is higher than the sum of square of the factor. The sum of square of factor is 1958. You can see here. And the sum of square, it is 5693. So basically, we see the how we calculate the ANOVA. So we calculate the ANOVA with between subject and within subject. Remember, in numerator, we take between subject, and in the denominator, we take within subject. In case of a repeated measure ANOVA, in denominator, we take residual. So that's why you will divide this mean square of repeated measure factor 1 with this residual to get this value of 3.4. That means 652 divided by 189, or the other way around, 995 by 289 if you are taking greenhouse gaser. We calculate F value in repeated measure like this because there is an error, and that's how we calculate it. Is it clear, Shweta? Oh, you have written, thank you. Okay, thank you. So now, have you understood up till this point? Then I'll go ahead. If someone can write yes or no. I think I have explained this Hunfeld also, corrections and assumptions. Now coming to this post hoc test. So post hoc test, I want a post hoc for repeated measure 1. So I have moved this factor to this box. And I want, you can apply good for Tukey's or Bonferroni. Both is okay. Bonferroni is more commonly used. And then coming to the estimated marginal mean. Remember, we discussed the concept of estimated marginal mean. So I will move this term here, estimated marginal mean. I'll click on this marginal mean plot and marginal mean tables. And then that confidence interval, which one of the participant was talking in the beginning, you can click it here, observed score, and then you can see the graph. So this is the post hoc. So you can see this is the post hoc, like systolic blood pressure in spring, comparison with the summer, autumn, and winter. This is summer and autumn and winter, and this is the various combinations. And here you can see that it is not significant. If you see the Bonferroni, it is not significant. Why? Because It is only the one value which is nearly significant, summer and autumn, where the mean difference is minus 14.9. And this difference is this first column minus this column. If you apply Tukey, you can see, if I have applied Tukey, then again you can see it has become a little more, this one has become significant. So this, the first one, this again summer and autumn. So depending on the corrections, you can see. And that's why you say that overall significant was not that much. If you take the greenhouse gazer, it was a very borderline one. If you take the first one, but again, this can be due to the smaller sample size. In actual data, like if you increase the number of sample size, then that is not there. So this is regarding, this is the marginal mean plot. Observed score I will remove because then other dots will appear. And this is the plot for the marginal mean. And this is the marginal mean. So if you see the marginal mean is 121.55 in the spring, 105 in summer, 120 in autumn, and 111 in winter. So this is the marginal mean, and this is the plot of this marginal mean. So how will you write the interpretation? So if you can write like this, let me show you. So you can write like the result of one-way repeated measure ANOVA that indicated a statistically significant variation in the systolic blood pressure across 4 seasons, and you have to write the degree of freedom. So both the degree of freedom of the error and that between subject factor, the F value and the P value. And then you will write about the post hoc also. If there is a no significance, then again you will write that it indicated there is no statistical significance, and then you have to write the degree of freedom. So remember, here you have to write the degree of freedom for the error. Now coming to the next question. So in this question, I have shown you this one. Does systolic blood pressure and pulse rate vary significantly among adult females over the 4 seasons? That is spring, summer, autumn, and winter. Now coming to the another one, next question, where we are showing you the interaction. So now my question is there any significant effect of gender on cognitive performance scores and quality of life scores at 3 different time points? Baseline, 1 month, and 3 months following a yoga intervention. So the intervention was yoga, and I have measured the cognitive performance and the quality of life at 3 different time points. Let's see how to see interaction in JAMOVI. So I'll open another data set. So this was the one. I'll show you the data. First, let me show you the variables. So this is the gender, age, and these are the 3 variables like cognitive performance score at baseline, cognitive performance score at 3 months, 1 month and 3 months, and the third one, which is the quality of life score. Now coming to this analysis, if you open this repeated measure, this is again open repeated measure ANOVA. So these are the 3 levels. So I'm not naming the levels now. You can name the levels first, but you can keep on entering, then these levels will be appearing here. Now, if I move this cognitive here, then you say that it has moved to this level 3 because this was active. So before moving, just see like which cell is active. So I have to move this in level 1. You cannot reverse the order. So I will move this to at 1 baseline, cognitive 2 at level 2, 1 month, and 3 at 1. Now I have to see the effect of gender. I want to see whether this improvement has got some effect with gender also, whether this improvement is same in male and female. So in this case, you can see there is a between subject factor. So in this between subject factor, I will enter this. So now, since this is active, I need to move this as an active one. So here, gender, move it to this one. And now again, partial eta square. So before we go, again, that assumption check you should do. So in this case, check with sphericity. And since there are two groups, you can check with the homogeneity and QQ plot also. Here also in type sum of square, you can see, you can click the type 3 sum of square. We have discussed that generally we use type 3 sum of squares. Now you can see repeated measure ANOVA. First, we check with the assumptions. So this, now what is your interpretation of this? This p-value 0.08. What is your interpretation? Is it significant or not significant? Or is the this thing assumption is met or not met? So Chandrasekhar, Rahul, Sumit, Shaq, Anuj. Okay. So assumption is met. You are right. Since p-value is more than 0.05, so the assumption is met. So if the assumption is met, should I click this sphericity correction or should I go with this none? What should be there? Yes, all of you? None. Right. So that's why I will not apply these corrections because my assumption is met. And if you come here, and if you see this is also, since the data point is less, but again, it is approximately normally distributed. I'm assuming that this is normal distribution. So I will not go for the Friedman. And coming to the homogeneity, you will see that homogeneity value, this is the Levine's test of homogeneity. Now, what is your interpretation for this? Those of you who have attended our previous webinar, is the assumption met or not met? Met. Yes, right. In today's webinar also we discussed, like if a named test is there and if the p-value is more than 0.05, then the assumption is met. So the homogeneity of variance assumption is also met. So I have checked with the assumptions. Now I'll go for the interpretation of this. Now you can see that this star, can you see in the first column, it will show you the repeated measure factor 1. This is significant, but the interaction of this repeated measure with gender, what is the p-value of this? It is 0.175. That means this is not a significant interaction. And you can see also. So then I will not report this. And I will write that this interaction was not significant. And I'll remove this gender and I may only report this. Or what you can do, if you see this estimated marginal mean, so what to do? First, you enter this factor 1 in term 1. In term 2, you enter 3. And in term 3, you have to select these two together. Then only there will be interaction. And then move these two together in term 3. And then you can click on this. This is already clicked. So you can see the plots also and the estimated marginal mean. This JAMOVI takes some time. You can see it is buffering. If I click on this error bar, so this you can see, it is almost parallel, not crossing. And that's why it was showing also in the above that this is not significant. If you remove this, then it will be much clearer the way we have shown you over that Excel. So this you can see, this is the plot of estimated marginal mean, which we discussed in our PowerPoint slides with that interaction effect. So here you can say it is almost parallel. That's why you will see that it is not there. Now, with the same example, I'll show you If you move this and if you take this quality of life, then you will find that quality of life score, it was significant. So this one and this. Again, gender, I'll keep it as such. And then you see the above plot. So here you will see that the interaction effect of this repeated measure and this gender, that is significant, 0.03. If it is significant, now you need to go for the post hoc and other analysis also. So this is same. Gender is there. So there I could not do that post hoc. Now you have to move this. You can check the post hoc for all three. And this is already there. Now how to interpret this? So just be attentive for a few more minutes, then we are done. So here you can see that this was significant. This we have seen. This sphericity test also we have seen. Coming to the post hoc. So this is the post hoc comparison of repeated measure factor 1. So if you focus on this table first, you can see it is showing you between the different season. So sorry, between the quality of life score at time point 1, 2, and 3. So this is the difference of 0.24 and 0.55 between 3 and it is 0.30. So this is easy to understand between the factor 1 and between the gender. The main problem is to interpret this table. Can you see this? This table, post hoc comparison of this gender. And this is called as the simple main effect. I'm not going into the, those of you who have done it on SPSS, you will see there we define two terms, main effect and simple main effect. Here we are not complicating that, but this table you need to interpret. And there are a lot of columns and rows you can see. Now what to interpret and how to see in this. So now what will you do? You will see, what is your goal? You have to see the post hoc comparison between male and female at each time point, right? So what you will do, you will see this one, this level 1. So I'm just, if you see this level 1 means in the beginning. So this is one, this male at this level 1 and female, because I want to see the gender. Let me move this, otherwise you will not see the significance level. Yes, this 2 keys. So this is at time point 1. So I will report this at one time point. The difference between the quality of life score is 0.8 and the p-value is not significant. Then at level 2, it is difference between male and female. It is again 0. There is no difference. And at time point 3, the difference is there, 0.34. But again, it is not significance. So remember, in one of the questions which we were asking you during the PowerPoint slides, that if there is an interaction, can you say that it is significant or not? So on the basis of plot, you cannot say. You have to say there is an interaction, but here you will see that the difference is not significant. So interaction only conveys that the values of this quality of life score, that is not same at each time point and gender, that is varying in the different gender, that means male and female, and that is varying at different time points also. So this is the interpretation of the interaction effect. Now, if you see the plot, so I'll go and show you the plot of estimated marginal mean. So you can see that this is crossing. So if the lines are crossing, or in other words, if they are not parallel, then on the basis of that, we can say that there is an interaction present. So you can just see the difference between the cognitive score. Remember, we have just entered the cognitive score and saw the plot. there the plot were almost parallel, and we have seen that there was no interaction. Here, there is an interaction, and you can see the plot also, it is crossing, so it is a significant interaction. And this is the marginal mean at each level, that means time point. Now, how to report it? So, for the reporting, you have to write that you conducted a repeated measure analysis of variance to examine the effect of gender on average cognitive performance score and quality of life score at 3 time points, wherever you are doing it. Here again, you will give the 2 degree of freedom and then the p-value. So you will give the p-value and degree of freedom for gender and time, both, and for the interaction also. So you can see here F1, F2, and then with the interaction effect. So you have to report this one. If I go up, you have to report this F value, this P value, degree of freedom and residual, again, this degree of freedom and residual, and this F value. And for the between subject also, which is the gender. So you have to report 3 F values, 3 pairs of this, not pair, 3 values of this F and P value. This interaction for gender and for time, which is the repeated measure factor in this case. So this is how we do the repeated measure analysis of variance with one between subject factor. And here we have taken, so we are not discussing, but those of you who are interested in doing the two-way repeated measure, then again you can, if you see this, you can see here, it is the main effect which we are seeing. If you want to do the two-way, three-way, and if you enter those variables here in the between subject, then together, then you can do the two-way analysis of variance also. But we are not covering that. We are restricting only the one-way analysis of variance without a between subject factor and one with between subject factor, the gender. So I hope most of the concepts are clear. Venkatesh and Dr. Shamshad and Venkatesh have posted the link for the previous webinars videos also, and for this video link also. The data sheet is there with you people. You can practice with that data sheet and you can see and you can write your own interpretation. Thank you so much. And I think over to Venkatesh.
Thank you so much, ma'am, for the wonderful session. I hope all our participants had benefited out of today's webinar immensely. We'll be sharing the certificates and the resource materials to the registered email ID in a week's time. If you have not received your previous certificates, kindly mail to support@clarinet.com with CC to us. We'll get it sorted. As ma'am said earlier, our next webinar of this series will be on September 12th on binomial logistic regression, the link of which also we'll be sharing shortly. As the last part of today's webinar, I would like to invite Dr. Samshad Ahmed sir, Associate Professor of the Department of Community and Family Medicine, AIIMS Patna, to deliver the vote of thanks.
Thank you, Venkatesh. And I would like to express my thanks to Dr. Pragya ma'am for her energetic session, as always, and to all the participants who joined our session and who are very regular to our session. And you also communicated that the next session is on logistic, and all the recordings and all the previous PPTs are available at our website. And I would like to request our participants that do join us in our next webinar on logistic regression. Thank you.
Thank you so much, sir. Thank you so much, ma'am. Team Clarinet, we are closing now.
Okay, sir. Okay. Thank you so much to all of you. Bye. I'm closing the session.